Imagine you press a button. A machine receives your command, processes it, and gives you an answer. You press the same button again. Same machine, same command, same everything. And the machine gives you a completely different answer. Not a wrong answer, not a glitch. A perfectly valid, entirely different answer. You stand there, staring at it, and you realize something deeply unsettling. By every law of logic you've ever understood, this second result should not exist. Bug in the software. It isn't a flaw in the hardware. It is a fundamental feature of the universe at the smallest possible scale. And once you understand it, you will never look at a computer or reality the same way again. Let's start at the very beginning. The classical computer sitting on your desk or the phone in your pocket works on a devastatingly simple principle. Everything it does, every email it sends, every video it plays, every calculation it performs, all of it, without exception, is built from a sequence of ones and zeros. A transistor is either on or it is off. A bit is either a 1 or it is 0. There is no in-between, there is no ambiguity, there is no question. And because of this, classical computers are perfectly, boringly deterministic. You give them the same input, they give you the same output, every single time. Without fail. That's not a limitation. That's the entire point. Reliability is the foundation of everything we've built with computers over the last 70 years. Quantum computers break this completely. A quantum computer does not use bits. It uses qubits, quantum bits. And a qubit doesn't have to choose between 0 and 1. A qubit can be both 0 and 1 at the same time. Not pretending to be both. Not switching between them so fast you can't tell. Actually, physically, genuinely both, simultaneously. This state is called superposition, and it is not a metaphor. It is not a convenient way of describing something we don't fully understand. It is a precisely measured, mathematically rigorous, experimentally verified property of quantum particles. A particle in superposition exists in multiple states at once, and that is simply what it does. Now here is where it gets strange. When you measure a qubit, when you actually look at it, when you try to extract an answer from it, the superposition collapses. The qubit is forced to choose. It becomes either a 0 or a 1. But here's the thing that should stop you cold. Which one it becomes is not. This is what physicists call the collapse of the wave function. And it is one of the most argued about, most philosophically explosive ideas in the history of science. The great Albert Einstein spent years insisting it couldn't be real. He famously refused to believe that God plays dice with the universe. He was wrong. Decades of experiments have confirmed it beyond any reasonable doubt. The universe does play dice, and quantum computers are the machines that have been built to harness that dice rolling. But let's make this concrete. Let's say you build a quantum circuit, a sequence of operations performed on qubits, to solve a specific problem. You prepare your qubits in a particular state. You run them through a series of quantum gates, which are the quantum equivalent of logic gates in classical computing. And at the end, you measure. The measurement collapses all your beautiful superpositions, and you get a string of zeros and ones, your answer. Now you run the exact same circuit again, same initial state. Same gates, same number of qubits. And you measure again, and you get a different string, a different answer. This isn't because something went wrong. This is because measurement collapse is inherently random. The universe looked at your qubits and made different choices the second time. And there is no physical law, no hidden variable, no deeper mechanism that forced it to choose the same way. The second result, the different one, was always a possibility. It was always sitting there in the probability distribution, waiting. This is the thing that breaks people's brains when they first encounter quantum computing. We are so deeply conditioned by our experience of classical machines, machines that are extensions of classical logic, of deterministic cause and effect, that a machine which gives different answers to the same question feels like a machine that's broken. It feels like a fundamental violation of what a computer is supposed to do. But a quantum computer isn't doing something wrong. It's doing something that classical computers literally cannot do. It's exploring a space of possibilities simultaneously, and when it's done, it has to pick one. And this is only the first reason the second result can differ. There are more. There are layers to this strangeness. The second reason is something called decoherence. And decoherence is, in many ways, the central villain of quantum computing. The thing that keeps engineers awake at night, the thing that has slowed the progress of this technology for decades, and the thing that the greatest minds in physics and engineering are currently racing to defeat. Here's the problem. Quantum states are extraordinarily fragile. The superposition of a qubit, that delicate, beautiful state of being both 0 and 1 at once, requires the qubit to be completely isolated from the rest of the universe. And the rest of the universe does not cooperate. The moment a qubit interacts with anything outside itself, a stray photon, a vibration in the material, a fluctuation in a magnetic field, even the faint hum of electromagnetic radiation from a device in the next room, that interaction carries information about the qubit's state away into the environment. And once information leaks out, the superposition is destroyed. The qubit becomes classical. It forgets that it was ever in a quantum state. This process is called decoherence, and it happens constantly, relentlessly, on timescales so short they are almost incomprehensible. The coherence time of a superconducting qubit, the window in which it can maintain its quantum state before the world destroys it, is measured in microseconds, millionths of a second. And in that tiny window, your quantum computer has to do all of its work: prepare the state, run the circuit, extract the answer. If it takes too long, or if the environment gets too noisy, the qubits decohere. They lose their quantum nature. The result you get is corrupted, shifted, randomized, wrong in ways that are subtle and hard to detect. Now imagine you run your circuit twice. The first time, the environmental noise is slightly lower. The second time, a tiny fluctuation, a thermal vibration at a scale you couldn't possibly measure or control, nudges one of your qubits just slightly out of alignment during the computation. The result is different. Not because the input changed, not because the algorithm changed, because the universe is noisy and quantum states are fragile. And the noise was different in those 2 microseconds than it was in the previous 2 microseconds. The second result should not exist, and yet there it is. The third source of variation is gate noise. Quantum gates are the operations performed on qubits during computation. They are implemented physically, typically using precisely calibrated pulses of microwave radiation aimed at superconducting circuits. The precision required is staggering. A pulse that is even slightly too long, or at a slightly wrong frequency, or with a slightly imperfect shape, will rotate the qubit by a slightly wrong angle. And in quantum mechanics, a slightly wrong angle cascades. Errors compound. A circuit that runs through hundreds or thousands of gates will accumulate noise from each imperfect operation, and by the time you measure, your answer has drifted from the truth by an amount that depends on the specific noise profile of that specific run. Run it again, and the noise is slightly different. The answer shifts. The fourth source, and this one is more statistical than physical, is shot noise. When you run a quantum computation, you don't just run it once, you run it many, many times and collect statistics. This is because a quantum measurement gives you one sample from a probability distribution. It doesn't give you the full distribution. To understand what your quantum computer is actually telling you, you need to run the same circuit hundreds or thousands of times, collect all the different outcomes, and look at the pattern. The most common outcome, the one that appears with the highest probability, is usually your answer. But shot noise is the uncertainty that arises from using a finite number of samples to estimate a probability distribution. If the true probability of the correct answer is 72%, and you run the circuit 100 times, you might observe it 68 times in one batch and 76 times in the next. The distribution you estimate is slightly different each time. So even if the physics were perfect, no decoherence, no gate noise, perfect measurement, you would still get slightly different distributions from run to run, simply because probability is probability, and finite sampling has inherent variance. Stack all 4 of these together, measurement collapse, decoherence, gate noise, shot noise, and you begin to understand why a quantum computer running the same circuit twice is almost guaranteed to produce different outputs. The second result doesn't just possibly exist. In most cases, the second result is inevitable. What changes is how different it is, and whether that difference matters for what you're trying to compute. And here is where the real genius of quantum computing reveals itself. Because the people building these machines are not trying to eliminate randomness. They know they can't. Randomness is not a bug in the quantum world. It is the operating principle. What they are trying to do is something far more subtle and far more powerful. They are trying to engineer the randomness so that the right answers are more likely than the wrong ones. This is called quantum interference. By designing the quantum circuit carefully, you can arrange for the probability waves of all the wrong answers to cancel each other out. Destructive interference, while the probability waves of the right answers reinforce each other. Constructive interference. At the end of the computation, you're left with a probability distribution that is heavily weighted toward the correct solution. This is not how classical computers work at all. A classical computer finds the right answer by explicitly computing it, by following a sequence of steps that leads with certainty to the result. A quantum computer finds the right answer by making it the most probable outcome. And that difference in strategy is what makes quantum computers potentially so much more powerful for certain types of problems. They don't search for answers one at a time. They explore the entire space of possible answers simultaneously in superposition, and then engineer the probability landscape so that the right answer rises to the surface. But to do this reliably, to actually use quantum computers for practical problems, not just demonstrations, you need to tame the noise. You need to build quantum systems that are stable enough, accurate enough, and large enough to solve problems that matter. And this is the war that is being fought right now in laboratories and data centers across the world with billions of dollars and some of the most brilliant minds of this generation. The weapon in this war is called quantum error correction. And it is one of the most beautiful ideas in the history of computation. The basic concept seems almost paradoxical at first. The problem is that qubits are fragile and noisy. The proposed solution is to use more qubits. The insight, and this took decades of theoretical work to establish rigorously, is that you can take a collection of many noisy physical qubits and encode them in a way that creates a single, more reliable logical qubit. The errors that affect individual physical qubits can be detected and corrected without ever actually measuring the qubit's value, without collapsing the superposition. This seems impossible, but it is not. It relies on the same quantum principles, entanglement, measurement, feedback, used in the computation itself. The history of this idea stretches back to the 1990s, when theorists first proved that error correction was possible in principle. For years, it remained largely theoretical. The engineering challenge was immense. Building physical systems with enough qubits, with low enough error rates, with fast enough control systems to detect and correct errors in real time. It required advances across physics, engineering, materials science, and classical computing simultaneously. Progress was slow, painfully slow. And then, in the last few years, something shifted. In late 2024, Google unveiled a quantum processor called Willow, and Willow did something that no quantum computer had done before. It demonstrated for the first time in history that error rates decreased exponentially as the number of qubits in the error correction code increased. In simpler terms, the bigger the system, the more reliable it became. This might sound obvious, but in the world of quantum computing, it was anything but. More qubits had always meant more chances for things to go wrong, more surface area for decoherence, more gate operations, each introducing more noise. The conventional wisdom was that scaling up quantum computers made them more error-prone, not less. Willow shattered that assumption. As Google scaled their surface code from a 3x3 grid of qubits to a 7x7 grid, the logical error rate dropped exponentially. They had crossed what physicists call the fault tolerance threshold, the point at which error correction starts to win the battle against noise. This was not a minor result. This was a proof of concept for the entire enterprise of fault-tolerant quantum computing. After nearly 30 years of theory, the hardware had finally caught up. The physical system was well-behaved enough, the error correction code was efficient enough, and the classical control systems were fast enough to detect and fix errors faster than they accumulated. The second result, the wrong one, the one that should not exist, could now be suppressed. Not eliminated, not in current hardware, but suppressed, made less likely, controlled. Then in November 2025, IBM announced its Nighthawk processor. 120 qubits, connected by 218 next-generation tunable couplers, capable of executing quantum circuits with over 5,000 2-qubit gates with relatively low error rates. IBM also revealed a new experimental chip called Quantum Loon, demonstrating all the key components needed for fully fault-tolerant computing. They announced a pathway to a processor that could run hundreds of millions of gates, the scale needed for the problems that actually matter: drug discovery, material science, financial modeling, climate simulation. IBM wasn't alone. Oxford Ionics, a company working with trapped ion qubits rather than superconducting circuits, announced in 2025 that they had achieved 99.99% fidelity on 2-qubit gate operations. This is an extraordinary number. It means that for every 10,000 quantum gate operations they perform, only one goes wrong. In the context of where quantum computing started, and where error rates were measured in percent, not fractions of a percent, this represents an improvement of orders of magnitude. And with error rates this low, the overhead required for error correction drops dramatically. Fewer physical qubits are needed to protect each logical qubit. The systems become more efficient, more scalable, more practical. Meanwhile, a company called Quera, working with neutral atom qubits, atoms cooled to near absolute zero and held in place by laser beams, announced a capability called magic states, a specific technical milestone required for universal fault-tolerant quantum computation. This is the kind of result that doesn't make headlines outside of physics journals, but within the field, it was enormous. Magic states are a resource, a specific type of quantum state that allows fault-tolerant quantum computers to perform a complete set of operations. Without them, a quantum computer can be error-corrected but not universal. With them, it can solve any problem in principle. Quera had taken a key step toward making their system complete. Fujitsu and Riken in Japan announced a 256-qubit superconducting quantum computer in April 2025, 4 times the size of their 2023 system, with plans for a 1,000-qubit machine by 2026. D-Wave, a company working on a fundamentally different approach called quantum annealing announced what it described as the world's first demonstration of quantum computational advantage on a real-world optimization problem, a result that sparked debate but also underscored how broadly the field had advanced. And on the software side, IBM's Qiskit framework showed a 24% increase in accuracy through improvements to dynamic circuit handling, while advances in error mitigation techniques reduced the classical computational cost of extracting accurate results from quantum hardware by a factor of more than 100. All of this was driven in part by a surge in research. The number of peer-reviewed papers on quantum error correction published in the first 10 months of 2025 alone exceeded 120, more than 3 times the total published in all of 2024. The field had entered a new phase, not just incremental progress, not just theoretical refinements, a genuine cascade of breakthroughs arriving faster than anyone expected. And yet, it's important to be honest about where we are. The quantum computers of today are still what engineers call NISQ devices, noisy, intermediate-scale quantum machines. They are powerful enough to demonstrate quantum principles, to run interesting experiments, to achieve supremacy on carefully constructed benchmark tasks, but they are not yet fault-tolerant. They cannot run the deep, complex circuits needed to break encryption or simulate large molecules or optimize global alignment supply chains. The noise is still too high. The qubit counts are still too low. The gap between what quantum computers can do today and what they will need to do to be genuinely transformative is real, and it is large. But for the first time in the history of the field, the path across that gap is clear. The theory is proven. The experimental results are pointing in the right direction. The engineering challenge is enormous but tractable. IBM has stated, with confidence, that they expect the wider research community to confirm the first verified quantum advantage, solving a real problem better than any classical method, by the end of 2026. Google's roadmap describes a system capable of running circuits with millions of gates on hundreds of logical qubits within the next few years. The error correction research that tripled in volume in 2025 is now feeding directly into hardware development cycles that are getting shorter and more aggressive. One of the more surprising developments of 2025 was the role artificial intelligence began playing in quantum error correction. Both IBM and Google started using small language models to monitor and calibrate qubit pulse sequences in real time, predicting when noise was about to spike and adjusting control signals to compensate before the error could propagate. This is a remarkable inversion. Classical AI helping quantum systems maintain their quantum nature. The machine learning models, trained on vast amounts of calibration data, can detect subtle drifts in qubit behavior that no human engineer could observe manually and respond to them in real time. This is not yet the full solution to the decoherence problem, but it represents a new tool in the arsenal, and an unexpected convergence between the two most transformative computing technologies of the era. There is also a theoretical dimension to all of this that deserves attention. Researchers in 2025 demonstrated that breaking RSA encryption, the cryptographic foundation of most modern internet security, might require only 1 million fault-tolerant logical qubits, dramatically fewer than the 20 million estimated just a few years ago. This is the kind of result that makes governments nervous. RSA encryption protects bank transactions, state secrets, military communications, medical records. A quantum computer powerful enough to break it would be among the most consequential technological events in history. And while that quantum computer does not exist today, the revised estimate of how many qubits it would require, combined with the pace at which qubit counts and error rates are improving, means the timeline is compressing. What was once thought to be a problem for the distant future is now a problem that the next generation of quantum hardware will begin to seriously approach. All of which brings us back to where we started. A quantum computer was run twice with the same input. The second result should not exist, and yet it does. What does that mean? It means that we are building machines that operate by the actual laws of physics, not the simplified, approximated classical laws that our intuitions are built from, but the deep, strange, probabilistic laws that govern reality at its most fundamental level. It means that computation, which we have always understood as a deterministic process, input leads to output, cause leads to effect, logic leads to truth, is actually capable of being something far stranger and far more powerful. It means that the randomness we have always tried to eliminate from our machines, the noise we have always treated as the enemy of precision, is in fact a resource. Harnessed correctly, controlled, carefully, engineered with enough precision, it becomes the mechanism by which quantum computers can explore spaces of possibility that classical computers cannot reach in any reasonable amount of time. The second result exists because the universe is not classical. We live in a quantum universe governed by probability amplitudes and wave functions and the collapse of superpositions. We built classical computers that deliberately ignore this fact, that operate in a regime where quantum effects are averaged out, where transistors behave like switches, where bits are bits and nothing more. And for 70 years, those classical computers have been enough. They have transformed civilization. They have put the sum of human knowledge in our pockets and connected every person on Earth and allowed us to simulate reality at scales our ancestors could not have imagined. But there are problems, important problems, crucial problems, that classical computers cannot solve. Not in principle, but in practice. Problems where the space of possible solutions is so vast that even the fastest classical supercomputer, running for longer than the age of the universe, could not search it exhaustively. The folding of proteins, the behavior of quantum materials, the optimization of systems with billions of interacting variables. For these problems, the deterministic march of classical logic is simply too slow. What is needed is a machine that can hold all the possibilities simultaneously. A machine that can explore the entire solution space at once in superposition, and then make the right answer the most likely one to emerge. That machine is a quantum computer, and the fact that it gives you a different answer the second time you run it isn't a problem to be apologized for. It is evidence that it is working, that it is genuinely operating in the quantum regime, genuinely using superposition and interference and entanglement to do something that no classical system can replicate. The second result should not exist by classical logic. But we do not live in a classical universe. We live in a quantum one. And we are finally, after decades of theory and engineering and failure and perseverance, building machines that are honest about that fact. The first quantum revolution, the understanding of quantum mechanics in the early 20th century, gave us lasers and semiconductors and MRI machines and nuclear power. It changed the world so completely that most people don't even think of it as a revolution anymore. It's just the background of modern life. The second quantum revolution, the one being fought right now in the cold chambers of quantum processors and the equations of error correction theorists and the calibration software of AI-assisted control systems, is just beginning. And when it arrives, the second result won't just be different. It will be exactly right in ways that no classical machine ever could be. Consider what that actually means in practice. Consider a pharmaceutical company trying to design a new antibiotic. Drug resistance is one of the great slow-motion crises of our time. Bacteria are evolving faster than we can design new drugs to fight them, and without effective antibiotics, routine surgeries and minor infections become life-threatening again. Designing a new antibiotic requires understanding how a drug molecule will interact with a bacterial enzyme, a quantum mechanical interaction, happening at the level of electrons and their probability distributions around atoms. Classical computers simulate this by making approximations. They treat the electrons as classical particles. They simplify the quantum behavior. They use models that are good enough to be useful but fundamentally wrong at the level of the physics. Quantum computers would simulate this the right way, using actual quantum mechanics to model actual quantum behavior, because they are themselves quantum systems. The simulation would be exact in ways that classical approximations simply cannot achieve. The difference between an approximate answer and an exact one in drug design can be the difference between a molecule that works and one that doesn't. It can be the difference between finding a drug in 5 years and finding it in 50. It can be measured in lives. Or consider the problem of climate. The atmosphere is a quantum system. The chemical reactions that create and destroy greenhouse gases, the splitting of methane, the oxidation of carbon, the catalytic processes that happen on the surfaces of aerosol particles, these are governed by quantum mechanics. Simulating them accurately requires quantum computation. The climate models we use today are the best we can build with classical hardware, and they are genuinely impressive, but they rely on parameterizations, on empirical corrections, on approximations that introduce uncertainties that compound over decades of simulation. A quantum computer running accurate molecular simulations could, in principle, eliminate entire categories of uncertainty from climate modeling. The predictions would be sharper, the interventions would be better targeted, the policy decisions would rest on firmer ground. Or consider finance. The optimization problems in modern portfolio management, in logistics networks, and energy grid balancing. These are problems where the number of possible configurations grows exponentially with the number of variables. A city trying to route hundreds of thousands of delivery vehicles. A power grid trying to balance supply and demand across thousands of nodes in real time. An investment bank trying to optimize a portfolio across thousands of correlated assets. These are problems where classical computers, even the most powerful ones available, reach the limits of what is computationally feasible. Quantum computers, exploiting superposition to explore all configurations simultaneously and interference to amplify the best solutions, could find optimal or near optimal answers to problems that are currently intractable. This is the promise. This is what all the noise, literal and figurative, is in service of. The second result, the strange one, the one that should not exist by classical logic, is the footprint of a machine that is doing something genuinely unprecedented, something that no device in the history of human civilization has ever done. It is computing in a mode that the universe itself permits, at the level where matter is not yet forced into classical definiteness, where possibility is still real and simultaneous and waiting to be measured. And when we learn to harness that mode fully, when the error rates fall low enough, when the qubit counts rise high enough, and the algorithms are clever enough, we will look back at the classical computer the way we look back at the abacus: useful, transformative for its time, and utterly insufficient for what came next. The second result should not exist, but it does. And in that impossibility is the most exciting sentence in the history of science. We were wrong about how the universe computes.